Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to talk about going beyond the basics with derivatives and learning about not all of them, but many of the extra styles of questions that can be asked. Now, if you look in your calculus textbook, you'll note that there are a lot of extra questions that perhaps your professor didn't cover. What your professor can only do is give you the tools to approach problems. It is your job to be able to think critically to actually do those problems on your own. And that's what separates calculus from many of its predecessors, right? So when you took algebra, you were shown every single skill and then you were basically mimicking or parroting what your instructor did. Calculus doesn't work that way. Calculus, you're given a set of tools and maybe a few examples that they can fit into the class time. And then you're given a lot of problems outside of class that look nothing like what you did in class. Trust me, they are actually the same problems, but some of them are not. So I shouldn't say they're all the same problem then. I should say most of them are similar to what your instructor did, but there are some that you have to think authentically and create your own mathematics. So let's see how some of these problems work. Let this function be this ugliness. And we actually faced this function in a previous video because this is a video in a series on finding derivatives of polynomials. So this should be your first time looking at derivatives of polynomials. You should already know how to take the derivative of a polynomial at this point, but that's about it. So here we go. Find a point or find points whose derivatives at those points are equal to 0. So what are they asking for here? Well, first thing they're asking us for is to take the derivative. So f prime, we need to find that derivative. And luckily, this problem we had actually done in a previous video, so I don't need to reinvent the wheel here. If you want to, you can go ahead and watch my video on computing derivatives of polynomials, but I'm going to just copy the end result here. And that was our end result right there. So now we need to figure out what we need to do with that. Find a point or some points A such that the derivative at those points is equal to 0. In other words, set f prime to equal 0. We're going to let f prime of x equal to 0 and solve. That's really all they're asking us to do. Take the derivative, set it equal to 0, and then solve. Graphically, what you're doing is you have some ugly function here, and it might look something like that. Who knows? Maybe it'll bounce back up here or whatever. But they're asking us to find out when the derivative is 0, when the tangent lines have slopes of 0. So you see what I'm highlighting here? I'm highlighting or writing down the points where we hit local maximums or local minimums is what we would call those in calculus or in all of mathematics. So that's what they're really asking us to find. When does this function have a local maximum or a local minimum, or possibly local maximums and minimums? Let's go ahead and do that. And by the way, that conversation about local maximums and local minimums is the purview of chapter 4 in the Stewart Calculus textbook. So just letting you know that will come back up if you're in my class. All right, letting f prime be 0, we get 0 is equal to x to the 3 halves, and now you're back to algebra. So from this point forward, there's no calculus. And in fact, because we had already pre-done this problem in the previous video, there's no calculus for us in this specific problem at all. But it's nice to see a review of some algebra concepts. So you can factor the right-hand side. Remember, when you factor something with a bunch of terms, if they have a common picture, which they do, x here, you factor out the lowest powered version of that common factor. So I'm going to factor out x to the negative 1/2. And you should have been doing this for at least 2 full semesters already in college algebra and pre-calculus, so I don't really have to go through all the steps. This will be an x squared minus 1/3 x minus 10/3. You could even factor out a third if you want to. I kind of want to, so I'm going to factor out a third. And some people will stare at this and go, why didn't he show his work on how he factored out x to the negative 1/2? And it's very similar to somebody asking, why didn't he show his work on how he factored out a 1/3? Or why didn't he show his work on how to add 7 plus 2? Those are all prerequisite skills. If I were to show my work on every little step, we'd be here for hours upon hours for a very simple problem. However, I will give you, or maybe point you to a tool that will help you out if you don't know how to factor out negative rational exponents. I have a video for my college algebra course, which is from 2 semesters below this course, and I think it's factoring negative rational exponents, factoring with negative rational exponents. So look through my playlist in college algebra, and you should be able to find it there. There might be a review of it in pre-calculus as well, but it's almost always factoring with negative rational exponents. So that's what you want to look for. Anyhow, moving forward, let's see if this trinomial factors. And again, I'm not going to magically show you how to factor a trinomial. If you want that, you could look at Khan Academy or some silliness like that. 2 numbers that multiply to 10 would be either 5 and 2 or 2 and 5. Let's see, that'd be 15 and 2. No, 6 and 5, yes. So I did the guess and check method here. You might want something different, right? So this is going to be a negative and positive. There, that's the method I use. I use a guess and check method. Again, I have videos on the guess and check method if you want to do that. Or you could use your box method, diamond method, AC method, whatever method you use for factoring. You're more than welcome to use it. All right. So let's take a look at when this equation is true. So you have 3 factors basically. This first factor, and then you have this second factor. And then you have, this third factor. And 3 factors multiplying to 0 implies that at least one of them must be 0. So either this guy would be 0, but there's no way for that guy to be 0. Don't think that letting x equal 0 will allow that guy to be 0, because x has a negative exponent. So that's actually 1 over the square root of x. You cannot allow x to be 0. So that is a big no-no. So I'm just going to go ahead and point it at it in red and say, nope. There's no way for x to be 0 there. The second possibility is that this is 0. 3x plus 5 is 0. Or in other words, x is equal to negative 5/3. And finally, the last one, x is equal to 2. No need for me to be slow with that. So those are the 2 points where our tangent lines have slope 0. Or in other words, those are the 2 points where the derivative is equal to a. So I can actually write that down as well. So f prime of a is 0 when a is negative 5/3 and when a is positive 2. Something I kind of dislike about this, I would normally say, thus f prime of x is equal to 0 when x is negative 5/3 and x is equal to 2. It's just I'm using the language they used. It's not that big of a deal. I would not mark somebody off if they wrote f prime of x is equal to 0 when x is equal to. They mean the same thing. So it's just a weird language issue. All right. So I hope that was okay. Let's see what we have coming up next. I think I only have 2 examples in this video. So the next one is find a second degree polynomial that satisfies the following 3 conditions. P of 2 is 5, P prime at 2 is 3, and P double prime at 2 is 2. Now we haven't actually done a lot of higher order derivative stuff here, so that's kind of nice to be able to do that now. So let's see, the second degree polynomial, we're going to let P of x just take the form of ax squared plus bx plus c. That's a second degree polynomial. They don't get much beefier or nicer than that. And we know one thing. We know that p of 2 has to be 5. But we also know that we want p prime at 2 to be 3 and p double prime at 2 to be 2. So what I'm going to do here, rather than just plugging in 2 into this polynomial and setting it equal to 5 right now, I'm just going to go ahead and start this problem by saying, okay, I need to write out what the polynomial initially looks like. I'll also eventually need its derivative, and I'll need its second derivative. So let's go ahead, and since we've written out the polynomial, let's go ahead and take its first derivative. Let me zoom out a little bit. All right, remember a, b, and c are just constants. They're numbers, we just don't know them yet. So taking the derivative of a times x squared, you would bring the 2 off the power of x and replace that with a power of 1. Taking the derivative of b times x, well, that'd be just b, right? Because the derivative of x is 1. And then the derivative of that constant c would be a 0, which you would not really write in because there's no need to. And then let's find the second derivative. It's supposed to be a double prime there. Sorry about that. Well, you have 2a and then the derivative of x. And the derivative of x is just 1. And then plus the derivative of a constant b, well, that's 0. Don't need to write that. All right. So let's go ahead now and insert our conditions. And this is kind of a foreshadowing of a big, massively important topic in Calculus 2 called Taylor polynomials. It is an amazing piece of calculus that if you happen to know the value of a function at a specific time, and the value of its derivative at the same time, and the value of its second derivative at the same time, you can start to recreate the polynomial. So if somebody came in and said, I have a function, and at time 2, it goes through a height of 5. So when x is 2, y is 5. There are an infinite number of functions that go through that have that behavior. But if you start to say, well, wait, I have more information. The derivative at time 2 is 3. All of a sudden, it really starts kind of giving a little bit of a better picture. So not only do you have this point in space, but its slope is 3. And then when somebody comes in, they say, but wait, I have one more piece of information. The second derivative at that moment is 2. That tells me something else about this point in space. It's slightly bowing up. You wouldn't know that from our experience so far, but that is actually what is happening. So it starts to kind of really form an accurate picture. Moreover, if you know for certain that the function you're dealing with has degree 2, and I give you 3 points, you will be able to identically find that function, that polynomial function. So let's do this. P prime, I'm going to start at the back end here because it's just easier. P double prime, of 2. Its output should be 2 when you plug 2 in. I'm going to do this. I'm going to write this in green. So this implies, well, P double prime of 2 equaling 2 implies that the output for this function right here will be 2 when my input for x is 2. Now, there is no x to input for in that function, so all I get here is that 2 is equal to 2a, but that is very helpful because now I know that a is 1. And now I'll go ahead and go to my next condition. P prime of 2 is equal to 3. So I'll just put here P prime of 2. Well, that's supposed to equal 3. That means that our output is 3 when our input is 2 for the derivative function. So let's see, that's 2 times a, but a, remember, is 1, times x, which we're plugging in 2 for, plus b. It's supposed to be a plus, I apologize. So all I'm doing is just stealing all the lettering here, right? You replace the output with the desired output, which I think was 3 in this case. You replace all x's with the desired input, which is 2. And if you know what a is or b is from previous work, you insert those as well. Well, we know what a is, it's 1. And so we get down to this picture right here. Subtracting 4 from both sides, you get that b is a -1. And now you move forward, and they gave us one final condition. It's this guy right here. And they told us the output should be, well, maybe I should say it this way. They told us that p of 2 is equal to 5, which tells us the output should be 5 whenever our inputs, our x values, are 2. So I have a times the x value, which is 2, squared, plus b, which is -1, times the x value, which is 2, plus c. Notice in this case, we only are missing one piece of information, that's c. So let's see, 4 minus 2 is 2. Subtract 2 from both sides, and you'll get that c is 3. Let me just double check my mathematics. 4 minus 2 is 2. Subtract 2. Yep, that's right. And so the question is, our question was, find a second degree polynomial that satisfies those 3 conditions. Well, we have. Our second degree polynomial is p of x is equal to 1x squared minus x and then plus 3. Very nicely done. Again, polynomials, this type of polynomial approximation and identification is critical as you move forward in calculus. It's one of the most important topics. So get used to it. I actually assign a project on this, or I try to in a normal semester. So I really dig it. I hope that wasn't too confusing. So that ends our discussion on the beyond the basics for derivatives of polynomials.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.